There are two different versions of the mean value theorem. There's the mean value theorem itself, and then there is the mean value theorem for integrals. Notice that if we just say the mean value theorem, this is the one we are talking about. So the mean value theorem says that if f is continuous and differentiable, there is a c value where f prime at c is equal to this little formula. In other words, there is a c value where the instantaneous rate of change is equal to the average rate of change, or the slope of the tangent line is equal to the slope of the secant line. Notice that the mean value theorem for integrals involves f at c, not f prime. Also notice that the mean value theorem for integrals only requires that f is continuous. It does not also have to be differentiable. Anyway, this theorem guarantees the existence of a number c where f at c is equal to this formula. This is the average value formula, which I abbreviate by saying the integral divided by the interval. In this video, we will take a function that is differentiable and continuous over a particular interval, and we will find the value of c whose existence is guaranteed by each of the mean value theorems. Let's start with the mean value theorem for derivatives. On the interval from 0 to 9, there is some c value where h prime at c is equal to h at 9 minus h at 0 divided by 9 minus 0. But this means h prime at c will equal the square root of 9 minus the square root of 0 divided by 9 minus 0. So h prime at c will equal 9 over 3, which simplifies to 1/3. Remembering that the square root of x is the same thing as x to the 1/2 power, h prime of x will equal 1/2 x to the negative 1/2 power. But this is the same thing as 1 over 2 times the square root of x. In that case, h prime at c will be 1 over 2 times the square root of c, which should equal 1/3 for some value c. We just need to solve for c. Let's take the reciprocal of both sides of this equation. That will give us 2 radical c is equal to 3. Dividing both sides by 2, we have radical c is equal to 3/2. If we square both sides of the equation, we get c is equal to 9 over 4. So this is the value of c whose existence is guaranteed by the mean value theorem, the one for derivatives. Now let's find the value of c whose existence is guaranteed by the mean value theorem for integrals. On the interval from 0 to 9, there is some c where h at c will equal the average value of h. That's the integral of h from 0 to 9 divided by the interval 9 minus 0. 9 minus 0 is just 9, and dividing by 9 is the same thing as multiplying by 1/9. So you will often see it written this way. H of x is the square root of x, which we can write as x to the 1/2 power. Let's go ahead and integrate by adding 1 to the exponent. That gives us the 3/2 power. Then we divide by the new exponent. Dividing by 3 over 2 is the same thing as multiplying by 2 over 3. Don't forget the 1/9 that we still have out in the front. We need to use the limits of integration, so we need to evaluate from 0 to 9. Multiplying 1/9 times 2/3, we get 2 over 27. Next, I will take the x to the 3/2 power, and I will find the value at 9 minus the value at 0. 0 to the 3/2 power is just 0. But looking at 9 to the 3/2 power, 3 is the power and 2 is the root. In other words, 9 to the 3/2 power is the same thing as the square root of 9 cubed. The square root of 9 is 3, and 3 cubed is 27. These 27s will cancel each other out, and we are left with h at c is equal to 2. Remember that h of x is the square root of x. So h at c will be the square root of c. So we have the square root of c is equal to 2. Squaring both sides, we get c is equal to 4. And this is the value of c that is guaranteed by the mean value theorem for integrals. So here is a new function and a new interval. Let's find the value of c whose existence is guaranteed by the mean value theorem for derivatives. F prime at c for some value c will equal f at 3 minus f at negative 3 divided by 3 minus negative 3. Substituting 3 in for x, we have 3 squared plus 2 times 3, so that's 9 plus 6, which is 15. Substituting negative 3 in for x, we get negative 3 squared plus 2 times negative 3, which is 9 minus 6, which is 3. So we have f prime at c equals 15 minus 3 divided by 3 plus 3. Of course, 3 minus negative 3 is the same as 3 plus 3. Therefore, f prime at c will equal 12 divided by 6, which is 2. Let's find f prime of x. By the power rule, we have 2x plus 2. Therefore, f prime at c will be 2c plus 2, and that should equal 2. Subtracting 2 from both sides, we have 2c is equal to 0, which means c is equal to 0. So this is the value of c guaranteed by the mean value theorem for derivatives. Now let's find the value of c whose existence is guaranteed by the mean value theorem for integrals. F at c for some value of c should equal the integral of x squared plus 2x dx from negative 3 to positive 3 divided by the interval 3 minus negative 3. Of course, 3 minus negative 3 is the same as 3 plus 3, which is 6. Dividing by 6 is the same as multiplying by 1/6, so I'm going to write it that way. Let's integrate term by term. Increasing the exponent by 1, we have x to the third power. Dividing by the new exponent, we have 1/3 x to the third power. Increasing this exponent by 1, we have x squared. But when we divide by the new exponent, 2 divided by 2 cancels out. So we just have plus x squared. We need to evaluate using the limits of integration. So from negative 3 to positive 3, which means we need to find the value at 3 minus the value at negative 3. So here we have the value at 3 minus the value at negative 3. Simplifying a little bit, 3 cubed is 27, 3 squared is 9, and negative 3 cubed is negative 27, negative 3 squared is 9. This simplifies to 1/6 times 9 plus 9 minus negative 9 plus 9. Negative 9 plus 9 is 0, so this will all be gone. So we end up with f at c is equal to 1/6 times 18. 18 divided by 6 is 3, so we have f at c is equal to 3. Remember that f of x is x squared plus 2x. So f at c will be c squared plus 2c, which equals 3. We need to solve for c, so let's subtract 3 from both sides and see if we can factor it. So c squared plus 2c minus 3 is equal to 0. Now, this looks factorable. C squared can only factor as c times c. 3 will only factor as 1 times 3. We are shooting for a middle of 2c, so we will need a negative 1c and a positive 3c. Using the zero product property, we can solve by setting c minus 1 equal to 0 and setting c plus 3 equal to 0. This will give us c is equal to 1 and c is equal to negative 3. Only one value of c was guaranteed by the mean value theorem for integrals, but we found 2. Sometimes they leave out this second one because negative 3 is one of the endpoints. So if you're doing a multiple choice question and they leave that one out, don't worry. But technically, they are both valid. Here is a new function and a new interval. Let's find the value of c guaranteed by the mean value theorem for derivatives. For some value of c, g prime at c will equal g at 4 minus g at 0 divided by 4 minus 0. So on the next step we have the cosine of 4 pi minus cosine 0 divided by 4 minus 0. Both 4 pi and 0 are over here on the right hand side of the unit circle where the value of cosine is 1. So we end up with g prime at c is equal to 1 minus 1 divided by 4 minus 0. So g prime at c is equal to 0. Remember that g of x is equal to the cosine of pi x. So what about g prime of x? Well, the derivative of cosine is negative sine, so I have negative sine of pi x, but because this is pi x and not just x, I need to do the chain rule and multiply by the derivative of pi x, which is pi. In other words, g prime of x is equal to negative pi times sine of pi x. In that case, g prime at c will be negative pi times the sine of pi c, and that is equal to 0. Now we just need to solve this equation for c. Let's start by dividing both sides of the equation by negative pi. So that will leave us with sine of pi c is equal to 0. Next, let's solve this equation for pi c. Where is sine equal to 0? Well, if we are thinking of one turn around the unit circle, sine will equal 0 at 0 and at pi. I'm leaving a little bit of extra space for extra solutions. I want to find all of the solutions that I can between 0 and 4. So there might be room for extra solutions. We can find extra solutions by adding 2 pi to the solutions that we already have. So 0 plus 2 pi is 2 pi, and pi plus 2 pi is 3 pi. Let's add 2 pi again, just in case there is space for even more solutions. If I take 2 pi plus another 2 pi, that's 4 pi. So I have 4 pi. If I do 3 pi plus 2 pi, that will be 5 pi. To solve for c, I need to divide each of these by pi. So c will equal 0 divided by pi, which is still 0. 2 pi divided by pi is 2. 4 pi divided by pi is 4. Pi divided by pi is 1. 3 pi divided by pi is 3. And 5 pi divided by pi is 5. Now, clearly some of these are outside of the interval, so we will simply cross those out. We want all solutions between 0 and 4, so that's going to just leave out, well, just 5. The mean value theorem for derivatives guaranteed the existence of one value of c, but here we have found 5 of them. Some people would cross out the 0 and the 4 because those are the endpoints, and that would leave you with a c value of 1, 2, or 3. Now let's find the value of c whose existence is guaranteed by the mean value theorem for integrals. For some c between 0 and 4, g at c is equal to the integral of g of x from 0 to 4 divided by the interval 4 minus 0. 4 minus 0 is just 4, and dividing by 4 is the same as multiplying by 1/4. I'm going to integrate cosine of pi x using some mental u substitution. If u is pi x, then the derivative of u is pi. That's going to show up as 1 over pi out in the front. So having done that, I can go ahead and take the antiderivative of cosine u, which is sine u. So I will have sine of pi x. And again, because it was not just an x, I had to take the derivative of pi x and then divide by that. So I will not forget my limits of integration from 0 to 4, and I will not forget that I have a 1/4 out in the front. To evaluate the sine of pi x from 0 to 4, I need to find the value at 4 minus the value at 0. Well, 0 and 4 pi are both over here on the right-hand side of the unit circle, where the value of sine is 0. So we have g at c is equal to 1 over 4 pi times 0 minus 0, which is 0. G of x is cosine of pi x, so g at c is cosine of pi c, and this is equal to 0. Let's go ahead and solve this equation for pi c. Ask yourself, where does cosine equal 0? If we were talking about one spin around the unit circle, cosine equals 0 at pi over 2 and at 3 pi over 2. Why am I leaving this additional space? We want to find all of the solutions that we can between 0 and 4. So there might be more solutions than these two. We can find additional solutions by adding 2 pi. And 2 pi is the same as 4 pi over 2. I'm thinking of it this way, so we will have like denominators. If I take pi over 2, and I add 4 pi over 2, then I'm going to get 5 pi over 2. If I do 3 pi over 2 plus 4 pi over 2, I get 7 pi over 2. Let's do one more just for fun. If I take 5 pi over 2 and add 4 pi over 2, I'm going to get 9 pi over 2. And if I do 7 pi over 2 plus 4 pi over 2, that's 11 pi over 2. To get c by itself, I need to divide both sides of the equation by pi. So, for my final answers, I'm going to divide each of these potential solutions by pi. So we have c is equal to all of these. Now, are any of these outside of the interval from 0 to 4? Well, 9 over 2 is 4.5, and 11 over 2 is 5.5. Well, we were guaranteed the existence of one value of c, and we found 4 of them. Here's a new function and a new interval. Let's find the value of c whose existence is guaranteed by the mean value theorem for derivatives. For some value c, f prime will equal j at 2 minus j at negative 2 divided by 2 minus negative 2. J at 2 equals 2 cubed plus 1, which equals 9. J at negative 2 equals negative 2 cubed plus 1, which equals negative 7. So f prime at c will equal 9 minus negative 7 divided by 2 minus negative 2, which means f prime at c will equal 9 plus 7, which is 16, divided by 2 plus 2, which is 4. So f prime at c will equal 4 for some value c. Oops, I just realized I've been saying f prime this whole time when I should have been saying j prime. Anyway, let's find j prime of x. So this will be 3x squared. That's j prime. In that case, j prime at c will be 3c squared. So 3c squared is equal to 4. Dividing both sides by 3, we have c squared is equal to 4/3. Taking the square root of both sides, we get c is equal to plus or minus 2 over the square root of 3. Only one value of c was guaranteed by the mean value theorem for derivatives, but we did find 2 of them. Now let's find the value of c whose existence is guaranteed by the mean value theorem for integrals. J at c for some value of c will equal the integral from negative 2 to positive 2 of x to the third power plus 1 dx divided by the interval 2 minus negative 2. This has a value of 4, and dividing by 4 is the same as multiplying by 1/4. So I'm going to write it that way just so it takes up a little bit less space. Integrating term by term, we increase the exponent by 1, so that's x to the fourth power. Then we divide by the new exponent, so we have 1/4 right here. And then the integral of 1 will simply become x. We need to evaluate from negative 2 to positive 2. So we need to find the value at 2 minus the value at negative 2. 2 to the fourth power is 16, and negative 2 to the fourth power is also 16. So we have this. 1/4 times 16 is 4, plus 2 is 6. 1/4 times 16 is 4, minus 2 is 2. So j at c is equal to 1/4 times 4, which is equal to 1. Remember that j of x is x to the third power plus 1. So j at c will be c to the third power plus 1, which will equal 1. Subtracting 1 from both sides, we have c to the third power is equal to 0, and then taking the cube root of both sides, we get c is equal to 0. This is the value of c that was guaranteed by the mean value theorem for integrals. Let's do one more. Here's a new function and a new interval. For this one, we are allowed to use a calculator. Let's start by typing k of x into the calculator in y equals under y1. So we have 1 over something. So I'm going to hit 1 and then alpha y equals enter to get the fraction going. And then it was 2 times the quantity x minus 2 squared. Let's start by finding the value of c whose existence is guaranteed by the mean value theorem for derivatives. On the interval from 4 to 6, there is some value of c where k prime at c is equal to k at 6 minus k at 4 divided by 6 minus 4. If I were feeling lazy, I could use my calculator to help me find k of 6 and k at 4. Keep in mind that we have k of x stored in y1. First, let's change one setting. So hit second window to access the table setup menu. Scroll down to where it says independent and switch from auto to ask. Once you've done that, hit second graph and notice how it says y1 right here. This tells you that whatever you type in for x, you're going to get the value for y1, which in this case is k of x. So if I want to find k at 6, I can just type in a 6. So k at 6 is 1 over 32, and k at 4 is 1 over 8. So now we have this. Of course, I could have found these values pretty quickly by hand. I could have found k at 6 like this, and I could have found k at 4 like this. Just to save space, instead of dividing by 2, I'm going to multiply by 1/2, which is the same thing. In order to have like denominators, let's multiply 1/8 by 4 over 4. So now we have this. Combining these like terms, I will have -3 over 32. And multiplying by 1/2, I get -3 over 64. Next, we need to find an expression for k prime of x. But first, we need to recognize that k of x itself is the same thing as 1/2 times x minus 2 to the -2 power. In this form, it's easier to do the power rule. So k prime is going to equal -2 times 1/2 is -1. And then we have the x minus 2. We reduce this power by 1, so we get the -3 power. Normally we would do the chain rule and multiply by the derivative of the inner function, but the derivative of x minus 2 is just 1, so there's nothing to multiply by. So this is k prime. Let's go ahead and write it without the negative exponent. So we have -1 over x minus 2 to the third power. This is k prime. If k prime of x is equal to -1 over x minus 2 to the third power, then k prime at c is going to equal -1 over c minus 2 to the third power. And k prime at c is equal to -3 over 64. Dividing both sides by -1, we get 1 over c minus 2 cubed is equal to 3 over 64. Taking the reciprocal of both sides, we have c minus 2 cubed is equal to 64 over 3. Taking the cube root of both sides of the equation, we have c minus 2 is equal to, well, the cube root of 64 is 4. So I'm just going to put 4 over the cube root of 3. Finally, adding 2 to both sides, we get c is equal to 2 plus 4 over the cube root of 3. It's a little bit ugly, but this is the value of c whose existence was guaranteed by the mean value theorem for derivatives. By the way, this is approximately equal to 4.773. Now let's find the value of c whose existence is guaranteed by the mean value theorem for integrals. On the closed interval from 4 to 6, there is some value of c where k at c is equal to the integral of k of x from 4 to 6 divided by the interval 6 minus 4. 6 minus 4 is 2. Dividing by 2 is the same as multiplying by 1/2, so I'm going to write it that way just to save some space. I think I really will use the calculator for this part. We could calculate this integral analytically, but hey, we're allowed to use the calculator, so let's do it. So we will say 1/2 times the integral, and for that we hit math, and we choose 9 for integral, and we're doing 4 to 6. And we want the integral of k of x, which remember we have that typed into y1. To access that, hit vars, switch over to the vars menu, choose option 1 for function, and pick y1. So this is the integral of k of x. And put your x in there, and kabam, 0.0625. Let's see if we can turn this into a nice fraction by hitting math, enter, enter. 1/16. So k at c is equal to 1/16 for some value of c. Let's find c. Remember that k of x is 1 over 2 times x minus 2 squared, so k at c will be 1 over 2 times c minus 2 squared. So now we have this. Taking the reciprocal of both sides of the equation, we have 2 times c minus 2 squared is equal to 16. Dividing both sides by 2, we have c minus 2 squared is equal to 8. Taking the square root of both sides, we have c minus 2 is equal to plus or minus the square root of 8. And adding 2 to both sides, we have c is equal to 2 plus or minus the square root of 8. Don't forget that we are looking for values of c between 4 and 6. 2 minus radical 8 is a negative number, so that's definitely outside of the interval. So we're going to have to stick with 2 plus radical 8 for the value of c that we are looking for. So as a decimal, the value of c guaranteed by the mean value theorem for integrals is 4.828.